Good afternoon or good morning to everyone, wherever you are. We are pleased to welcome everyone for this week's Math-Physics seminar. We have Sebastian Heller from Leibniz University of Hannover. He will give a talk on real holomorphic sections of Deligne-Hitchin moduli spaces and integrable PDEs. Floor is yours, Sebastian.
Thank you very much for the invitation and for the kind introduction. Of course, I would prefer to be in Bengaluru another time, but it's also nice to give a talk in front of you in online and see some well-known faces to myself. So, for example, I saw Arpan. So I will talk about real holomorphic sections of the Deligne-Hitchin moduli spaces and their relationship to integrable PDEs, partial differential equations. Most of them will be of quite geometric type. And this is based on various works. Most of them are joined with co-authors, for example, Lynn Heller, and also with work with Indranil Biswas and Markus Roeser. And I should also mention that the images I will show are all produced by Nicola Schmidt. So I will start with some well-known things. Maybe the first non-trivial nonlinear geometric PDE was the Liouville equation, which somehow shows up when you study classical minimal surfaces in R3. So here you see an example. It's the famous Shirk surface, the desingularization of two perpendicularly intersecting planes. And when you study minimal surfaces, people realized a long time ago that it's quite useful to use complex analytic data to describe them, and you get the spinor representation, and in terms of that you can somehow describe all the classical invariants of surfaces like first and second fundamental form. In particular, you can describe the conformal metric and in terms of conformal coordinate on your surface. So if the metric is just given by so the induced metric should be G is e to the 2u times the standard Euclidean metric on the domain where you parameterize your surface, then the conformal factor satisfies this linear equation, the Liouville equation. Laplace u is 2 times e to the minus 2u times the length of a holomorphic function, which is basically the Hopf differential of the surface. So the Hopf differential is somehow the 2-0 part of the second fundamental form. And if you have a minimal surface, mean curvature is 0, of course. So the 2-0 part and the 0-2 part give the whole second fundamental form, and because it's a real valued symmetric linear form, the 2-0 part determines the whole second fundamental form. So the Hopf differential determines the second fundamental form, and the conformal factor determines the first fundamental form. So we have all the information to describe a surface in free states. And then from complex analysis, you know how to write down the general solution of such kind of equation in terms of holomorphic data. Namely, you get two holomorphic functions on the domain f and g, such that f times the derivative of g is this holomorphic function q times dz, where z is the conformal coordinate. And then e to the 2u, so the conformal factor is determined by this formula here. So in this very simple situation, you can somehow solve nonlinear PDEs in terms of holomorphic data. And this has then been generalized to other situations. So let me just describe one particular instance where this works really nicely. So it's that of the so-called Cinchgordon equation. and it occurs with different signs. So there are basically two main important sub cases. One is that of minimal tori in the free sphere. So the equations are different for surfaces in R3 and S3, of course. Yeah, the equations for minimal surfaces in the free sphere become much harder to study. But in that case, still we get some relationship to holomorphic data. And I will explain how this works in a second. So, but let me just say what the image here is. So it's a parameterization of the famous Clifford torus, which is then, of course, very graphically projected to R3. So it's a minimal surface in the free sphere, and the Willmore minimizer. So the Willmore functional somehow measures how round the surface is, and it's the surface, the unique compact surface in free space, which minimizes the Willmore energy among all surfaces which have genus at least one. And so this is one type of a Cinchgordon equation which plays an important role in geometry. The other one is that of course, constant negative curvature metrics, and particularly on tori. So yeah, let me write down the equations for these two cases. So I hope you see the color here. So we have two different possible signs. So the black, the plus, the black color is that for minimal tori in the free sphere, and the red one is that for constant negative curvature metrics on tori. And due to the sign, you get a lot of different behavior. So for example, yeah, on tori, you get quite nice global solutions of that equation for the plus sign, while the minus sign has singularities usually. But still there's a strong relationship between both cases. Namely, you can describe them in terms of holomorphic data. So what you do is, yeah, you can somehow define a so-called spectral curve associated to the solution of this PDE. And this spectral curve yeah, is equipped with some additional data. And then you can prove in the end that these solutions on tori, so the so-called finite gap solutions, are yeah, can be parameterized in terms of theta functions on the associated spectral curve. And in particular, simple subcases, it even reduces to the yeah, Weierstrass P function, so it even simplifies. But in general, the formulas, of course, become quite complicated, but still you get a complex analytic way of describing solutions of these partial differential equations, which is quite interesting, at least for me, and is used quite often in mathematical physics to describe certain types of solutions of related equations. So yeah, so the goal of my talk is to explain how similar things can be done in the case of compact Riemann surfaces of higher genus, or likewise, you could also generalize to Riemann surfaces with punctures where, yeah, where you study parabolic structures instead of, yeah.
Sebastian,
so yes,
would you like to take questions in the middle or reserve?
Yes, I'm very happy about questions. Sorry, I should have said so. So please.
No, that's perfectly fine. So I think Arpan has a question. Arpan, do you want to go ahead and ask your question?
Hello, can you hear me?
Yes.
Yeah.
Okay, my video just okay. Yeah. No, my question was that so you talked about constant negative curvature metrics on tori, but isn't that obstructed by the Gauss-Bonnet theorem?
Oh yeah, you get singularities. Yes.
Okay.
Yes, you get singularities, but still you get some kind of solutions to these equations away from the singularity. And
okay, thanks.
somehow you still get some kind of Gauss-Bonnet if you take a certain renormalization of that singularities.
Okay, thanks.
So any other questions at the moment?
Yeah, I have a question. When you say you have constant negative curvature and you also have a conformal factor, what does it exactly mean?
So yeah, on the torus,
because the conformal factor, there could be a non-trivial curvature, I would suppose. No?
Yes. In general, you have a non-trivial curvature. So you start at the torus of any conformal type, and you have the flat metric, and then you look for metrics which are given by G is e to the 2u times the flat metric on the torus, and yeah, then you can produce examples where the metric is has negative curvature. So there's a particular nice geometric way of doing that. So let me just draw a picture. So yeah, think of the hyperbolic space separated by the S1 here. And here we have another hyperbolic space I denote by H minus. And then you can somehow look at a projective structure on the torus whose developing map somehow is basically given by you go along here. So this the developing map along one generator of a fundamental group has no monodromy, and for the second you have monodromy. And but the monodromy is real. So you get a developing map which gives you a well-defined metric on the torus of constant negative curvature away from these two closed singular curves. So that's a particular nice example of such kind of a metric. And yeah, I hope.
But away from the singular curves, you are saying it's constant negative curvature. And at the
yes, exactly.
Curve.
Yes.
Okay.
Yes, it has constant negative curvature. So yeah, I will come back to these kinds of singularities later in my talk. So let me just continue if explaining what the goals here are. So I just said I want to treat these geometric PDEs in terms of, or some cases of geometric PDEs in terms of complex analytic data, and yeah, the type of the PDEs I have to restrict to are so-called integrable PDEs. So they admit many symmetries. So in the case of the minimal surfaces in free space, there's this well-known construction of the associated family of minimal surfaces, which is obtained by rotating the Hopf differential, basically. So yeah, another way of looking at this is the Weierstrass representation. So the differential is given by the real part of a holomorphic differential on your surface, and you can of course rotate the complex valued holomorphic differential by a factor of length 1, and doing that gives you the associated family. And for example, it somehow it deforms the catenoid into the I'm not that good in drawing, so I'm particularly happy about the pictures, into the helicoid. So yeah, that's some kind of a internal symmetry of that PDE, that you have this associated family of minimal surfaces. So in the case of tori, you usually have lax pairs which describe your solutions. And in general, if you, or all the PDEs I'm studying in this talk are related to associated families of flat connections. So I will explain that in a second, but it's at the moment it's good enough to think about this associated family of flat connections as a direct generalization of this associated family of minimal surfaces, of a minimal surface in R3. So it gives you not only one solution, but a whole family as one family of solutions to the same PDE. And this structure can be used to incorporate complex geometry. So that's the goal of my talk today. And somehow interestingly, the way this works is via another integrable PDE, namely the famous Hitchin self-duality equations. So so the setup, at least for this talk here, is the following. I consider a compact Riemann surface sigma and a Hermitian vector bundle. And then I study unitary connections on this vector bundle. So unitary, of course, with respect to the Hermitian metric, and Higgs fields. So they are given by holomorphic one forms, so complex 1-0 forms with values in the trace-free endomorphism bundle. And holomorphic means that I consider the induced holomorphic structure from the connection nabla. So with respect to this just means that either you take the induced 0-1 operator del bar nabla, and then del bar nabla phi is 0, or likewise if you have locally I guess this is the best way of doing that. So this gives you the holomorphicity condition just written down here. And then the self-duality equations are
Is phi a scalar?
No. It's phi is not a scalar. It's a 1-0 form. So k is the complex tangent bundle of the Riemann surface, cotangent bundle, of course. Sorry, and SL means the trace-free endomorphism bundles. So it's some kind of a associated tensor field. So in particular, we do not get that everything commutes. So the self-duality equation then is an equation for the relating the curvature with the Higgs field phi, and the second equation is this just mentioned holomorphicity equation. So the first equation tells us that the curvature of nabla plus phi plus phi star is actually flat. So having unitarity and the second equation, this gives us that the connection nabla plus phi star is flat. So the curvature is vanishing. And actually, having that the connection is unitary and we have a Hermitian bundle, we can even go further and introduce a spectral parameter, lambda inverse and lambda here. And then it turns out that all these connections for all lambda on the unit circle and then for all lambda in the complex punctured plane will be flat in the end. So this is the type of integrability for the PDE, for the Hitchin self-duality equations, which we will use later on. So that's the self-duality equation. Yes.
So H0, what does H0 signify? Does it mean 0 forms?
No. It's maybe the notation is not so good. H0 means holomorphic, so it's basically this equation written in another way. So H0 means it's a holomorphic section in this bundle here. And of course, the canonical bundle has a natural induced holomorphic structure, and the Hermitian bundle V also has a natural induced holomorphic structure, namely from the connection nabla, or the 0-1 part of the connection nabla. And H0 just denotes it's a holomorphic section in that bundle. So we have two types of equations for the self-duality equations. One is just this holomorphicity, the second equation here, and the other one is this unitarity or the curvature equation. Does this answer your question?
Yeah.
So then the first observation basically is that you get a gauge group action which preserves solutions. So if you start with a solution and apply a unitary gauge transformation, you get a new solution. And likewise, if you consider a complexified gauge transformation, so not a gauge transformation which is unitary with respect to the Hermitian structure, but it's just a gauge of the bundle, then you will still get a new solution of the self-duality equations, but with respect to a different Hermitian metric. So we have that action, and we shall make use of that in a second to somehow reduce everything to a finite dimensional space. But let me first mention two important or famous and important results of Hitchin. Namely, the first is that a solution of the self-duality equation is actually determined by the Higgs pair. So basically you can forget about the Hermitian metric, and the Hitchin-Kobayashi correspondence tells you that there's a unique Hermitian metric such that you get a solution of the self-duality equation, provided the Higgs pair is stable. So a natural generalization of the stability notion for holomorphic structures, which takes the Higgs field phi into account. So from a certain point of view, you forget about the Hermitian metric, so of basically half the data of your solutions, but it's still enough to obtain to have at least implicitly by solving a PDE the full solution of the self-duality equations. And this is one way where you already see somehow that complex geometry shows up. And a second observation, I think this was original due to Simon Donaldson, is that the solution is also determined by the monodromy of this flat connection, nabla plus phi star. So it's a flat connection. It gives you a monodromy representation of the Riemann surface, and this monodromy representation determines the solution of the self-duality equations. So again, you somehow forget about the Hermitian metric on the bundle and just look at this flat connection here. At this flat connection, and it by solving a geometric PDE, it contains all the information. So what you then get in the end is a moduli space. I call it the self-duality moduli space. So it's the space of solutions modulo gauge transformation, and it's a finite dimensional space. So it depends. The dimension depends on the genus of the Riemann surface and on the rank of the bundle, of course. But that shouldn't matter so much.
Sebastian, quick question.
Yes.
So the Riemann-Hilbert map gives you a way to go between the flat connection and the monodromy, right?
Yes, exactly.
So what is the additional thing that's required to get Donaldson's result?
So you need the Riemann surface structure.
Okay.
So the result is basically take any irreducible connection on your Riemann surface, on a given Riemann surface. Then there's a unique Hermitian structure on your bundle such that you can decompose. So let's denote the original connection by head nabla. So given this head nabla or nabla head on the Riemann surface, there's a unique Hermitian metric such that you can split in this way, where phi satisfies the second equation here.
Okay, I see.
So right, that's the that's the Donaldson result, and in particular, it tells you, or it's basically equivalent to the fact that your solution gives you an equivariant harmonic map into a certain non-compact symmetric space. And the splitting somehow tells you that your Hermitian metric is a harmonic metric. So it's a harmonicity equation that you have to solve at that point.
So the del nabla phi equation is like a covariant derivative?
It's
a covariant derivative for the connection as well as the metric or something like that?
I mean, it's a 0-1 part of a covariant derivative. So at least on our Riemann surface. So phi is a 1-0 form, right? By construction. So or by definition, because it's K is the space of 1-0 forms. So if we take the exterior derivative with respect to the connection of phi, we just get the del bar derivative. So the exterior derivative with respect of this one form with respect to nabla is just the holomorphic derivative, the 0-1 derivative of this phi. So in local coordinates, if you want, you do write phi is some matrix aij times the dz, and the bundle should be trivialized with respect to the holomorphic frame of the bundle, and then the equation del bar nabla phi is locally equivalent to just the ordinary del bar, so the 0-1 part of the derivative of these functions aij, wedge dz. So this guy is 0 if and only if the aij's are holomorphic. So with respect to a holomorphic frame and with respect to a holomorphic chart set, it just means that your Higgs field phi is holomorphic. That's the equation del bar nabla phi is 0.
And the curvature part is taken care of by the holomorphicity.
No. They are two a priori unrelated equations. So the curvature part is a totally different equation.
No, but when you're talking about a covariant derivative, shouldn't you also consider the entire gamut of curvature as well as the connection?
No.
Usually because when you consider, say, the covariant derivative for the Yang-Mills field in a curved space, you consider the curvature part as well as the Yang-Mills part, right? So here, what's the analog of that?
I mean, the equation, of course, depends on the holomorphic bundle type. So for example, if the connection nabla induces a stable holomorphic bundle, then you already know that there's a certain space of Higgs fields. You exactly know the dimension, and but it's really another type of equation, because you just look for holomorphicity. It doesn't. I mean, that's basically some part of the content of Hitchin's paper, that you have these different points of view. You have this geometric point of view by looking at the curvature equation, a reduction of the Yang-Mills equation to Riemann surfaces, and then you have the point of view from Higgs bundles. You just look at the holomorphic equation. So there's no curvature showing up, and but of course the bundle type of the holomorphic bundle type of phi shows up and plays a role. but you don't see any curvature in this second equation.
So the holomorphic bundle takes care of the curvature part. That's what you're saying.
I mean, yeah, in the end, it's a result of Hitchin that if you have a holomorphic bundle and this holomorphic Higgs field satisfying stability, then you get the emission metric, and therefore you get a unitary connection which has curvature and so on. Right. But only by solving this corresponding self-duality equations.
Okay.
So yeah, what you get in the end is this finite dimensional modelized space of solutions. So yeah, usually denoted by MSD for self-duality equation, and it has different types of complex structures. So, for example, from the Higgs bundle point of view, so from looking at from looking just at the holomorphic bundle and the holomorphic Higgs field, what we get is this complex structure I. So yeah, you directly see that it's a complex manifold by going through that quotient construction. And there's a different way of introducing a complex structure, namely if you look at the flat connection nabla plus phi star. So then you have the Riemann-Hilbert correspondence to representation into the corresponding complex group, and this gives you complex space and a complex manifold if you stay away from irreducible points. So it was proven by Hitchin that actually I and J are anti-commuting, so the product of these two gives a third complex structure K. So you have a bunch of complex structures, and actually what you get in the end is a hyper-kahler space. So there's also a natural L2 metric by integrating up certain pieces of natural tangent vectors, so infinitesimal variations of your PDEs here. And this gives you, by integrating up, this gives you a nice metric, which turns out to be hyper-kahler. So it means it is kahler for all these complex structures, which is a very important type of a metric. For example, it's automatically Ricci flat and carries a lot of interesting structure. And additionally, what we also get is some integrable system structures for the complex structure I. So if we look at the Higgs field, we forget about the Hermitian metric. We can compute the invariance of the Higgs field phi, so traces and higher order traces. And this turns out to be an integrable system structure on this modelized space of solutions of the self-duality equations. So, for example, the generic fiber of this map here is a torus, complex torus, and the metric, the hyper-kahler metric, can be described at least far out by corrections of that semi-flat metric, which you get from the integrable system structures. So so there's a lot of interesting structures on this modelized space, the important point for us here is another construction by Hitchin with some collaborators, namely the twistor space construction for hyper-kahler manifold. So this works generally if you start with a hyper-kahler manifold. So just a manifold M with a Riemannian metric, which is kahler for three anti-commuting complex structures. So you have I, J, and K, as in the example of the self-duality solutions, and you have a metric which is which is kahler for each of these complex structures. And then you can associate a complex analytic space, which has some kind of additional structures, which contains all the information about this metric and this hyper-kahler space. And the starting point is to define the complex structure on the product of M with CP1. So you think of you identify the two sphere with CP1 in the standard way. And then on the space P, you define a almost complex structure as follows. So the tangent space at a point P with in M and X, Y, Z, so three real numbers whose square sums up to 1, P. So this can be described, of course, as the tangent space of M times the tangent space of CP1 or S2 at this point. And then you define the complex structure to be X times the first complex structure I here plus Y times the second complex structure J plus Z times the third complex structure K on this summand. And here you take the natural complex structure on the two sphere identified with CP1. So this gives you an almost complex structure I on this manifold P. And it turns out that the hyper-kahler property tells you that I on the space P is actually a complex manifold. So it's integrable, the complex structure I. So it's not almost complex, but actually a complex structure. And we get a complex manifold P. And we get a we get a holomorphic fibration by forgetting about the base point. So it gives us a holomorphic fibration over CP1. And we have additional data which can be used to recover the remaining metric. For example, there's some kind of so-called twisted relative holomorphic symplectic form. It's a holomorphic section in a certain bundle which gives you a symplectic form on all the fibers of this fibration. So the fibers are basically the complex manifold M with respect to a specific complex structure in this two sphere full of different complex structures. And we have a holomorphic symplectic form for all these fibers, which is packed together in this twisted holomorphic symplectic form. And what is also important is a real structure, which looks quite simple. So it's just given by this map here. If their lambda goes to minus lambda bar inverse is of course the antipodal involution of the two sphere. And by construction of the complex structure on P, this is actually a real structure. So it's anti-holomorphic, and of course it squares to minus identity. And then we also have the so-called twistor lines. They are holomorphic sections of this fibration P to CP1 by taking spectral parameter lambda in CP1 and map it to the point P and lambda, which is an element in our manifold P. And this is a holomorphic line, and it's real in that sense that if I denote this section here by S, then I have tau of S of lambda is the same as S of minus lambda bar inverse. So that's the reality condition I mean here. So it's somehow invariant or equivariant with respect to the real structure tau. And from these data, one can recover all the data of the hyper-kahler manifold, and this so in a certain sense, one can construct the hyper-kahler metric from complex analytic data from P and this twisted symplectic form together with some kind of reality conditions. So this works in general, but it becomes particularly nice in the case in specific cases. For example, in the case of the self-duality equations. And this was introduced by Deligne and worked out by Simpson, and uses the notation of lambda-connections. So a lambda connection is somehow a generalization of an ordinary flat connection in the following way. So it's given by a triple consisting of some complex number and a holomorphic structure on the bundle V. So for me, a holomorphic structure is usually an operator which maps sections. So a first order linear differential operator which maps sections of the bundle V into 0-1 forms with values in the bundle V, satisfying the 0-1 part of the Leibniz rule. So del bar Fs, so F is a function, S is a section, is so I take the 0-1 part of the derivative times S plus F del bar S. And then the space of holomorphic sections of this bundle V is just the kernel of this del bar operator. So that's, at least in the case of Riemann surfaces, a one-to-one correspondence between the structure of a holomorphic vector bundle V on a complex vector bundle and these del bar operators, which are elliptic first order partial differential operators. So this is the yes.
Sorry, may I ask a question, please?
Sure.
Is there an analog of this? For the Euclidean space, the twistor space is defined via certain incidence relations and then a reality condition. So, is there an analog of incidence relations here for this more complicated space?
Good question. So, I mean, it's really hard to work out what the complex twistor space of the self-duality solutions really is. So basically, you cannot somehow describe it as explicitly as in the case of the Euclidean space, for example. Unfortunately. So I don't think it's possible at the moment. But in certain specific examples, you can do that. So if for example you just look at line bundle connections, basically you get the standard abelian Hodge theory, and you can use that to write down the twistor space, which is of course quite boring because you basically have a quotient of the twistor space of the flat space, and then you can work out everything. But in the interesting cases of higher ranked bundles, it's basically at the moment impossible, unfortunately. But good description is very desirable for many reasons. So the third ingredient of a lambda. Yes, sure.
So what is the difference between a section and a function on a curved space?
Oh, a section. I have a complex vector bundle V. So the section is a map from sigma into this vector bundle V, which projects to the identity, while a function is just a map into complex numbers or real numbers. So sections for me are usually maps into the vector bundle.
But when you define the derivative on a section times a function, why do you need to have a product of a section and a function in order to define the derivative? You can
no. It's an additional condition. So you want some kind of Leibniz rule for any kind of derivative. So if you have any section you would like to know, how to compute what happens if you have a related section which is just given by multiplying that section with a function. And these conditions, the Leibniz rules, tell you how to relate the different derivatives. So it's a quite natural and important condition, which
So by holomorphic vector bundle, you mean something like a connection in physics, right?
It's so with del bar operator, it's something like a connection, but only half of the information of a connection. So the connection gives you really the full derivative, while the holomorphic structure of this del bar operator only gives you the somehow complex antilinear part of the derivative. Like
why is that sufficient? Why is that sufficient?
Oh, I mean, it depends on what you want to do, but it turns out that this is a good notion because it describes the space of holomorphic bundles quite well. So if you think of a holomorphic bundle as a bundle whose transition functions are given by holomorphic cocycles, this has a natural del bar operator. And conversely, if you have some such kind of del bar operator, so the 0-1 part of connection, this gives you a holomorphic vector bundle structure. So it gives you cocycles which are holomorphic. So in that sense, it's a good notation. But there are also other instances. So maybe the easiest one is the Cauchy-Riemann differential equations. So one way of writing that is you look for functions in a complex domain or Riemann surface into C. And of course, you can take the derivative. But then if you look at the 0-1 part of the derivative, which I usually denote by this del bar F, then the Cauchy-Riemann equation just tells us this should be 0. So in that sense, it's a natural notion because it's somehow just the generalization of the Cauchy-Riemann differential operator. And it's somehow it's 1/2 of the ordinary differential, or on vector bundles and on curved spaces, it's somehow 1/2 of a connection, of an ordinary connection.
And when you're defining the covariant derivative, are you saying that this is the covariant derivative or the ordinary derivative?
It's usually for me it's a covariant derivative, but the covariant derivative satisfies a Leibniz rule, which takes into account the standard derivative.
But the covariant derivative usually doesn't satisfy the Cauchy-Riemann equation. It's the ordinary derivative.
No, it satisfies. No, of course not. But somehow if you look at
talk.
Sorry?
Yeah, I think we should reserve maybe longer discussions for the end. We should let Sebastian proceed with the main content of his talk.
What I wanted to say is that the third ingredient of the holomorphic of a lambda connection is a first order differential operator D, which satisfied a rescaled version, and here I should write 1-0, of the Leibniz rule. So it's not it's not an ordinary Leibniz rule, but we just rescale it by this complex number lambda. And additionally, we have a condition which tells us basically that it's analogous to flatness of a connection. And I will explain in a second why this holds. But it's a very mild generalization of a connection, but it's a very useful generalization, as we will see in a second. So let me give a few examples. So the first example is that of when lambda is 0, then the first equation tells us that the first order differential operator is actually tensorial, so it's a Higgs field. And the second equation tells us it's holomorphic, so it's really a holomorphic Higgs field. And in the second case, when lambda is 1, we can sum up the holomorphic structure and the differential operator D. And this is actually a connection because del bar satisfies the 0-1 Leibniz rule, D satisfies for lambda is 1 the 1-0 Leibniz rule. So the sum satisfies the Leibniz rule, and therefore it's a connection. And the second equation tells us it's a flat connection. So yeah, we can generalize for all lambda not equal to 0 and get flat connections. So in a certain way, this notion naturally generalizes between is some kind of interpolation between Higgs fields at lambda 0, so the complex structure I on the modelized space, and at lambda is 1 between flat connections, so the complex structure J. Okay, and yeah, one can use that to define a natural quotient, the so-called Hodge modelized space, by the gauge group action. So one looks at lambda connections, modulo this gauge group action, and one gets again a finite dimensional manifold. And because the gauge group doesn't affect anyhow the lambda, we have a natural projection to the complex numbers. So if we do that, we can do the same thing for the complex conjugate Riemann surface. So sigma bar. So if you think of sigma complex manifold of dimension 1 with complex structure I, then sigma bar has complex structure minus I. Or if you think about Riemann surfaces as defined by algebraic equations, you get the complex conjugate algebraic equation. So the complex conjugate Riemann surface also has this so-called Hodge modelized space. And you have a natural way of gluing these Hodge modelized spaces over C star by this simple, somehow looking formula. So we just move lambda to 1 over lambda. We change D and del bar by rescaling them because the 0-1 forms on sigma are just the 1-0 forms on sigma bar. So 1-0 on sigma is basically the same thing as 1-0 on sigma bar and vice versa. So this tells us that we get a lambda connection. So this formula 1 over lambda D and 1 over lambda del bar is actually a 1 over lambda connection on the complex conjugate Riemann surface. And we get a way of gluing the modelized space. And this gives us a vibration over CP1. And the important thing is that this space, I should somehow guess I should hurry a little bit. This space is actually the
actually, Sebastian, just to
yes?
Since there was a long sort of digression, feel free to take your time. It's okay.
Okay, thanks a lot. So I can explain this slide.
Please,
I'm happy.
Proceed as you would have under normal situations.
So the theorem, which was basically written up by Simpson, but the main motivation behind this definition is that this glued copies of the Hodge modelized space, which give us the Deligne-Hitchin modelized space, is actually the twistor space of the modelized space of solutions of the self-duality equations. So there's a complex analytic way of describing the modelized space, which is not very explicit, but still we have a nice complex analytic way using this notion of lambda connections. And in the way this works is by as a complex manifold. It's just the modelized space of lambda connections, and we have to somehow specify what are the real structures, and they are also given quite natural. So the first thing is that we have a C star action on this space just by scaling the lambda and the D part of the connection. So this gives us a well-defined C star action. Then we have a real structure coming from the Hermitian metric, basically. So it's denoted by rho because it's not the twistor real structure, but will play a role later in the last few minutes. So it's just given by basically looking at the adjoint operators with respect to the Hermitian metric, and on the complex Riemann surface sigma bar. So in the same way you get from from any connection on a vector bundle, you get the adjoint connection. You get from a del bar operator the adjoint del bar operator, but this adjoint del bar operator is not a 0-1 operator, but a 1-0 operator. But we already observed that 1-0 is the same as 0-1 on sigma bar. So actually this formula here is really well defined and gives us a map between the Deligne-Hitchin moduli space to itself, but it's of course a real structure. So it's anti-holomorphic and squares to identity. And then the complex structure, the twistor complex structure tau, is just given by the composition of this real structure with the multiplication by mu is equal to -1. And yeah, so the real structure rho covers lambda goes to lambda bar inverse. So this tau actually, as by definition, covers the antipodal map, lambda goes to minus lambda bar inverse. And in fact, by the result of Simpson, this is the twistor real structure. And now comes the important part for me. We also are able to specify the twistor lines. They are given by an associated family of flat connections. One I wrote down before, and I see that I have a typo here, unfortunately. Here should be plus. So yeah, for example, at lambda is 1, we get somehow by identifying lambda connections for lambda is 1 with flat connections, we just get the flat connection nabla, so del bar nabla plus del nabla plus phi star, which is the one considered by Donaldson. And for lambda is 0, this part here vanishes and this part here vanishes, and we get the Higgs field. And actually the whole twistor line is given by this associated family of flat connections. So yeah, let me explain some theorems by myself. So there was a question by Simpson whether all real holomorphic sections of this twistor space are actually solutions of the self-duality equations or twistor lines. And the answer is no. There are other sections which are not global solutions of the self-duality equations. So yeah, they satisfy reality conditions. They are holomorphic sections, but they are not global solutions, but only solutions of the self-duality equations away from one-dimensional singularity sets. So similar to the case of the metric of constant negative curvature, we have one-dimensional singularity sets where the solution tends to infinity, and yeah, this is also what the picture is showing here. So solutions of a self-duality equation can be seen in the rank 2 case as harmonic maps to hyperbolic free space. And the picture here shows shows a two-sphere. The grid is a two-sphere. Inside is a hyperbolic space, and outside is a second copy of the hyperbolic space. And the surface you see is a harmonic map into this hyperbolic free space, which intersects the boundary along certain curves you see indicated here. So it becomes singular along certain curves of the Riemann surface and continues as a harmonic map outside in another copy of the hyperbolic space, and then goes back in and out and so on. So these are these are basically the same type of sections as the twistor lines, but are actually different because they have singular solutions. And yeah, actually we proved, or I proved with Indranil and Markus Roeser, the existence of other type of real holomorphic sections, which are not related to self-duality equations at all, but to equivariant harmonic maps into the two spheres sitting inside the deSitter free space. So yeah, I guess a natural question then is how to distinguish these different cases. So particularly the case of self-duality equations, which are singular, and non-singular self-duality equations, the standard ones, but also these type of real solutions with which go into the deSitter space. And the way you do that is by associating signs to real holomorphic sections. So this works as follows. So you take a section and you lift it in terms of families of flat connections. So you have to prove that, but there's always a way to obtain such kind of lift near lambda 0, which somehow encounters the behavior at lambda 0, so that you have really a section in the Deligne-Hitchin moduli space which extends holomorphically to lambda 0. And you do the same at infinity. And between these two lifts by construction, because you have the moduli space, you need to have gauge transformations. So this gives you a family of gauge transformations, G of lambda, depending holomorphically on the spectral parameter lambda. And you can see the sign and therefore the solution in terms of properties of this G of lambda. So a reality condition, either for tau, or you can do the same thing for rho, gives you a certain identity of this G. But this identity is not unique, but depends on a sign in rank 2 case, or for higher rank vector bundles, you have certain roots of identity here, which gives you other kind of solutions. And this sign determines what kind of solution of or what kind of geometric PDE you solve. And the way you solve this is by Birkhoff factorization, loop group factorization. So yeah, I'm running out of time, so I shouldn't go too much into detail of that. But you have a
Sebastian, feel free to take time. It's okay. Take how much of your time.
So you have that G of lambda depends holomorphically on lambda, but of course it's not well defined at lambda 0 and it's not well defined at lambda's infinity. So what you do is you want to factor that into a plus part. So it's a holomorphic family of gauge transformations which extends holomorphically to lambda 0 times a holomorphic family of gauge transformations which extends holomorphically to infinity. So if you have this Birkhoff factorization, then you can prove that this nabla lambda times G plus of lambda is actually an associated family of a harmonic map. And you, if you look careful at that, you directly obtain a solution of the corresponding geometric PDE. The problem is that this factorization does not always exist. It might fail sometimes. And this is basically the reason for singularities. So whenever this factorization works, you get a global solution. But if this factorization doesn't work globally on your Riemann surface, then you get usually singular solutions. And this gives you the following cases, at least in the SL2C case. So we have a twistor complex anti-holomorphic structure tau, and we have a plus sign. And then we get harmonic maps to H3 or solutions of the self-duality equations, but they might have singularities, exactly where the factorization doesn't work. So the twistor lines, so the actual solution of the self-duality equations are exactly those guys where we have the global Birkhoff factorization into positive and negative part. And then the harmonic map is a harmonic map into hyperbolic free space, or you can identify it with the space SL2C mod SU2 because it parameterizes all the Hermitian metrics on a rank 2 vector space. So the slightly different case is that of the same real structure, but we have minus identity in this equation for this gauge transformation, and this gives us a different type of solutions of the self-duality of a PDE. So it's a self-duality equation with a sign, or you can think of it as a singular harmonic map into DeSitter free space, which is now SL2C mod SU11. So basically, if you think, if you want, it's an SU11 self-duality solution. So there are two other situations, namely the complex, the anti-holomorphic structure rho, and plus identity. And here we get harmonic maps into SU2. And we do not get any singularities, which is interesting. But in this very case, you always have a global factorization. That's a theorem you have to prove, but it works in this setup, which is nice and which is somehow exceptional. And it's a counterpart to the difference between existence result for harmonic maps into negatively curved spaces and between harmonic maps into positive curved spaces. So in negative curved spaces, we always have some kind of existence in each homotopy class and so on. Somehow all these good analytic properties of solutions. But from this Deligne-Hitchin setup, you get somehow singularities by producing solutions with these signs. But the thing is opposite if you look for harmonic maps into S3. Then the analytic side is good. So not all families like maps have a nice limit and so on. But
Sebastian, your audio was
has a better.
Your audio was breaking up.
My audio was
maybe.
Okay. Is
maybe
it better now?
Yeah, it's better now. You might want to just repeat whatever you said.
Okay, so the analytic point of view on harmonic maps into hyperbolic space is much better than this complex analytic point of view. And conversely, or vice versa, the analytic investigation of harmonic maps into compact symmetric spaces like the free sphere is quite complicated, and you get into singularities, while from this complex analytic point of view through Deligne-Hitchin modelized spaces and sections thereof, you have a very nice result that you always get solutions without self-equations from these kind of sections. So, and then there's the last case, which somehow parameterizes singular harmonic maps to anti-deSitter space, and likewise, minimal, or as a special case, minimal surfaces in anti-deSitter free space, which of course play a role in ADS CFT correspondence. So it's all these different cases show up here in a natural way, and you get solutions to these equations by looking at holomorphic sections of these Deligne-Hitchin modelized spaces with certain reality conditions. And you can also see some kind of symmetries between these different cases. So for example, it's well known that the Cinchgordon equation for negatively curved metrics of constant curvature, say -1, is related to minimal surface equation for surfaces in anti-deSitter free space. And through that business of looking at the sections of the Deligne-Hitchin modelized spaces, you directly see that relationship due to intrinsic symmetries of certain sections. So it's a quite appropriate space to study these kind of questions. And I just want to mention that you get similar results for higher rank. So for example, in SL3C, you get as subclasses the hyperbolic and the elliptic affine spheres, which are also distinguished by signs, and you get minimal Lagrangian surfaces and so on. So you have all these kinds of structures and solutions of PDEs in terms of complex analytic data, basically in terms of these holomorphic sections of a complex vibration. And that's somehow the counterpart of these finite gap spectral curve theory for solutions of on tori to the case of higher genus Riemann surfaces. And I guess I should stop now, but I would like to stop. Sorry, I would like to stop with a nice picture. So these are basically showing surfaces in which in the free sphere which are related to harmonic maps into the free sphere, and they come from sections again in these Deligne-Hitchin modulized spaces. So yeah, thank you very much for your attention, and yeah, please ask further questions.
Thank you. Thank you, Sebastian. First, let's thank the speaker for a wonderful talk. And now, of course, you can
I ask
to
a question?
questions. Yes, please.
Yeah. So a couple of questions. First of all, do you also get CMC surfaces? And second question is, do you get completely new integrable systems this way?
So yeah, for the first question, yes. So CMC surfaces, I mean, for example, in R3, they are related to harmonic maps into the two-sphere sitting inside S3. So we, yeah, looking at the two-sphere and harmonic maps into that, we get sections of the Deligne-Hitchin moduli space, and we can reproduce these CMC surfaces from that. And the same works in S3. And actually, that's yeah, that's how we do all these kinds of surfaces. We really produce some kind of families of flat connections, which are basically the lifts of sections in the Deligne-Hitchin moduli spaces, satisfying these kind of reality conditions, and we compute the surfaces in that way. So yeah, that's the case. So for the second question, so the question was about whether we see some kind of new type of equations.
Yes.
Geometric PDEs.
Completely
so,
new kind of, yeah.
Okay. At the very moment, not, I would say, because I mean, yeah, one of the main reasons is my own limitation. So far I just did work in rank 2 and rank 3 case, and I plan to do some work in the rank 4 case related to Wilmore surfaces then. But yeah, I mean, people studied these situations for a long time and somehow worked out basically all the interesting PDEs a long time ago already. So I wouldn't think that I find out any new type of equation, but what I find out is a new way of describing these solutions of these equations globally on compact Riemann surfaces of higher genus, and also to prove existence of new surfaces. So that's yeah, another thing that we can do. Actually, we prove existence of certain kind of solutions, which give us much more information about the solutions than the somehow more classical, older existence proof of solutions through PDE methods. So, for example, yeah, in the free sphere, you know the existence of minimal surfaces by solving plateau solutions and gluing that together, but you have not much information about what the properties of these solutions are. And we can do things like that using this setup, because everything, yeah, at limit points in yeah, everything becomes quite explicit, and you can somehow evolve these kinds of solutions and get families of solutions and compute data implicitly, at least to some order.
Mm-hmm. Thank you. Thank you very much.
So I had a couple of questions. So in each of the cases that you outlined, you have a hyper-kahler space, right? So there is some...
No.
No?
So you mean I should go. You mean these
Say
cases
for
here?
SL2, yeah, SL2, yeah.
No, it's not true. I mean, you get different kind of structures on the moduli space, but it's not true that you always get hyper-kahler structures. So, for example, in the case of harmonic maps to S3, you would get what Hitchin introduced as hypersymplectic manifolds. So no very natural metric. In the case of harmonic maps to a deSitter free space, I think you get a hyper-kahler matrix with a split signature.
Oh, I see.
But yeah, what I showed is that for the self-duality equations, if you look at different components which have singularities, you still get hyper-kahler manifolds with positive signature. So you get some kind of new hyper-kahler spaces which are not known yet, which come from these singular solutions of the self-duality equations and really are have hyper-kahler structure. And we want to do some kind of simple example for tori where we want to work out what kind of hyper-kahler space that is. We haven't finished that yet, but it might be related to some known hyper-kahler manifolds, four manifolds in this case of tori. But on a general genus G Riemann surface, you would get quite complicated spaces.
And when you say self-duality equations with singularities, are they similar to like the kind of singularities you get when you introduce parabolic structures for Higgs bundles, or these are different?
It's different because the singularities are along one-dimensional real lines.
Okay, right. So they're not
like
at points. Okay.
They're not points. So in that sense, it's quite different. But I mean, it doesn't work yet. But I think there should be some kind of relationship. So it might be if you think of a family of Riemann surfaces and you get a singularity along a closed loop, and you deform the Riemann surface type such that the loop shrinks and you get a degeneration of conformal types on the Riemann surfaces. It might be that the limit has to do with somehow parabolic Higgs bundles and solutions of parabolic Higgs bundles. I have a vague feeling, but I haven't proven anything in that direction. But in that sense, it might be that there's a relationship. But at the very moment, the singularities are still quite different.
Nice. Thanks.
I have a question. Okay, so if I understand correctly, if you don't impose the reality structure on the sections, then the space of sections, it forms a complex hyper-kahler space. Is that correct?
Actually, it's somehow a complexification of the space of real sections, and as such, it has a natural hyper-kahler structure, at least on some neighborhood of the real section. So yes, that's correct. So you have a complex manifold, and itself it has again a hyper-kahler structure. Yes.
Is there a natural interpretation of this complex hyper-kahler manifold formed by the space of sections as the tangent bundle of some complex symplectic manifold?
I guess you can somehow do locally the identification. So one way of introducing the hyper-kahler structure would be to go through this Goethe-Fikes, and I think the other was Kaladin construction. That's one way, but actually it simplifies in this setup. So you can show the existence of this, I would say formal hyper-kahler structure, because you have to take care that everything is non-degenerate and so on, of course. You can do that more directly in this case of twistor spaces or sections of twistor spaces with a C star action. And the thing is, I guess, that you can naturally write down family of or a symplectic form on this space of sections, which somehow can then be used to construct a hyper-kahler metric. So it is a particular instance of this construction you mentioned, so the Fikes construction on the cotangent space, but it somehow simplifies. But for for all twistor spaces of hyper-kahler manifolds with these star actions in particular for this setup.
Okay. Yeah. Perhaps I should mention the motivation for that question. It's because there was this recent work of Bridgeland and Strahan on constructing a complex hyper-kahler manifold from a complex symplectic manifold plus some additional data of a Joyce structure, so to say, like some local function. And using that, they define a complex hyper-kahler structure on the tangent space of the complex symplectic structure. And the connection to real hyper-kahler structures is not completely understood. Like it's believed that on some real slice, it should be the usual story of a real hyper-kahler structure existing on the tangent space of a special Kahler manifold. But yeah, but I don't think any concrete examples are really known. It would be nice that if Deligne-Hitchin modelized, the space of sections of the Deligne-Hitchin modelized space could be realized as
so which paper of Bridgeland is that? I should definitely have a look into that.
This is it's a pretty recent paper. Like Strahan is spelled like S-T-R-A-C-H-A-N. Ian Strahan, yeah. And
I guess I will find it. Otherwise, I will just write an email.
Yeah, sure, yeah. Okay, but yeah, that's it. Yeah, thanks.
Any other questions? Okay, so if not, we'll thank Sebastian one more time, and
I have a quick question, Ashwin. Sorry.
Oh yeah, please go ahead. Please
this is a general question about integrable systems. Flatness of a connection generally gives you an integrability of the PDEs, right? The flatness of the connection.
The flatness of the whole family.
Whole family of connections with the structural parameter, right? Yeah. So can you always write the lax pair from there, or it's not always possible?
I mean,
supposing you just have the flatness of a certain connection with a spectral parameter thrown in, can you write the lax pair for the integrable systems from there, or that's not really possible?
I mean, yeah, some people would say the family of flat connections is already the Lux pair, but somehow in this more classical sense, you would like to reduce to finite dimensionals, and yeah, so for example, the Lux pair for harmonic tori and things like that, which I guess you know quite well. This doesn't generalize, at least yet, to this point.
Okay, yeah.
Unfortunately, but of course that would be nice and interesting.
Okay, all right. Thank you so much. Thank you for a wonderful talk.
Thank you.
Okay, so I'll again wait to see if there are questions. I don't see any hands. So yeah, so let's go ahead and thank Sebastian. I'll leave the Zoom call on, of course, but I'll just stop the recording after we thank him. Okay.
So, was very nice.